Hello everyone. In this video, we're going to be solving a system of differential equations. As promised before, I'll try to bring you a system or an equation every week and try to make it harder, which is not always going to work, but I'll try to bump it up in level of difficulty. Okay, so we have this system where we have dx over dt equals x plus e to the power t, and dy over dt is y plus x. So one thing to notice about this system, because y and x are functions of t, that's what we're going to try to solve for, right? The first equation does not contain any y. That's a good thing, okay? That'll make the system a lot easier. And obviously, we tackled equations that have x and y mixed in them, and we're going to be doing even more complicated ones. I'm also planning to start a course, maybe a series of videos on partial differential equations, along with a little bit of lecture notes, not necessarily a whole course, but maybe to talk about some basics and standard methods. So let's go ahead and see how we can solve a problem like this. As I said earlier, there's no y in the first equation. By the way, when I say first equation, I'm referring to the first one that I wrote here, dx over dt, and the other one is the second one. So for simplicity's sake, I'm going to go ahead and use a notation here. Instead of dx over dt, I'm going to use x prime. This is by no means the derivative of x with respect to x, because that will be 1. This is the derivative of x with respect to t. Does that make sense? X prime is dx over dt, y prime is dy over dt, because they're both functions of t. Okay? Obviously, y and x can be indirectly related, but that's not our goal. Our goal is to solve for x and y in terms of t. Okay, so from the first equation, which is this one, we can actually go ahead and subtract x first so that we can kind of bring these two on the same side. And notice that instead of, if we had a 0 instead of e to the power t, then this would be a homogeneous equation, right? But this is non-homogeneous. But guess what? To be able to solve it, we need to find the solution to the homogeneous equation first. Because what happens is, with non-homogeneous equations, the general solution is made up of two pieces. One of them is going to be the homogeneous solution. The other one is just going to be a particular solution, which you can find by assuming some certain type of function, so on and so forth. Or, if you can make this an exact equation, you can also look at it that way. That's what we're going to do, because I want to try something new. And to make it exact, if it's not already exact, and what I mean by exact is, you'll see in a little bit, it's the derivative of something, usually a product. But looks like this is not like that, right? It's not the derivative of a product or a quotient. So how do we turn it into one? By using what's called an integrating factor. So here's what we're going to do. We're going to multiply both sides by e to the power negative 1, okay? That's going to give us e to the power negative 1 times x prime minus x times, by the way, you could also write it this way, I guess, x prime times e to the power negative t minus e to the power negative t times x. And that is going to equal, what is e to the power negative t times e to the t? That's e to the power 0, or just 1. Great. Now, if you take a look at this closely, and in this case, I used the integrating factor e to the power negative t, and you'll notice that this is actually the derivative of something, like a product. Why? Because look, this is x, okay, and e to the negative t being multiplied together. If you differentiate this, you're going to get the derivative of x multiplied by the second function, which is this. And then the derivative of the second function, which is with the minus sign, of course, this, times the first function, which is x. There you go. So by multiplying by e to the power negative t, we made it an exact equation so that we can directly integrate. Does that make sense? And obviously, 1 is the derivative of what? T plus c1, right? And c1 is a constant here. Why do I use c1? Because we'll probably have more constants. I'm going to call them c2. At the end, maybe I can combine them into c. Doesn't matter what you use, but as long as it's a constant. So now what we need to do is wait a minute. I meant that this is the derivative of t plus c1. Okay, we haven't integrated both sides yet. Now, if you do, you're basically going to be removing the derivatives. So in other words, you're going to have x times e to the negative t equals t plus c1. And I don't need to add a constant because I already did. Great. So this is the answer. No, because we need to solve for x. Let's go ahead and multiply both sides by e to the t again. So it's going to look like this. E to the t multiplied by t plus c sub 1. So that is the solution for x. Like I said earlier, there's no y. So solving for x is actually pretty easy. Again, you can solve for the homogeneous version and then go for a particular solution. By the way, to solve for homogeneous, you're basically going to try something like x equals e to the power kt. When you plug it into this, you should be getting two roots from here, which are going to give you k minus 1 equals 0, which is k equals 1. So that's going to give you only one solution, which is e to the power t, okay? With a constant, of course. That's what we got here. Now, let's go ahead and solve for y now. And if you remember, y prime is y plus x. The good thing is we can go ahead and subtract y from both sides and replace x with what it is. What is x? We know that because we solved the first equation. It's e to the t multiplied by t plus c sub 1. Awesome. Now, what are we going to do for this? Again, the same idea. Look at the left-hand side. It's the same pattern with x prime minus x. Now we have y prime minus y. So what's going to happen? This is actually going to be the derivative of y times e to the power negative t. But only after you multiply both sides by e to the negative t. So let's go ahead and do that. And then that'll be exact. And this will be t plus c1. And now we can basically write this as y times e to the power negative t, the derivative of that equals, okay, now here's what we need to do. We need to write this as the derivative of something. In other words, we are integrating. Does that make sense? So this is the derivative of what? If you don't want to do that, you can go and write it like this and then integrate both sides. Of course, when you integrate the derivative of something, you're going to end up with that thing, right? And when you integrate the right-hand side here, what's the integral of t? Remember the power rule. You increase the power, divide by that, t squared divided by 2. c1 is just a constant, so it'll be multiplied by t, because think about it. c1 is the derivative of what? c1t, right? Like 2 is the derivative of what? 2t, or 2x, right? Plus, you do need another constant. Again, the same thing is going to apply. Multiply both sides by e to the t, and you're going to get something like e to the t multiply by t squared divided by 2 plus c1t. And if you want to write the 1/2, like follow the same pattern, 1/2 of t squared plus c1 times t plus c2, you'll get the solution for y. Let's go ahead and copy the solution for x, so that way we have the whole thing together. And remember, x was e to the t times t plus c1. And this gives us the whole solution set. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out SyberMath, the Shorts channel, and aplusbi. And bye-bye.